Hello everyone, my name is Mama Arisakama Jeffrey, and today I would like to teach you guys about chapter 2, which is we're gonna start with definition of statements. So, what is mathematical statement? Mathematical statement is a declarative or any expressions that may contain any words and symbol. For example, x plus 2 equals to 5, and the value, like the statement is true if the x value is 3 and false otherwise. And then x plus 10 equal to 9 plus 9. So this statement is actually true. And the last one is 12 minus 1 greater than 12 multiplied by 2. So from this statement, we can say that the statement is false because 12 multiplied by 2 is not like 12 minus 1. Compound statement. What is compound statement? So, compound statement is a statement that it is not the case of proposition. For example, let P and Q be a propositions. P, tomorrow is Sunday. Q, tomorrow is not Sunday. Okay? So we can use both of these on truth table. Like the table that show above. P, true, false. Q, false, true. Converse. I would like to explain to you guys about converse. For implication P implies Q. What is the converse for the implications? So the converse of the implication is Q implies P. Okay? For example, let's say P, she is hungry, while Q, she ate. So the implication P implies Q is if she is hungry, then she eats. While the converse of the implication is Q implies P. So we can say if she eat, then she is hungry. So that is the converse for the implications. Contrapositive. So what is contrapositive? For implication P implies Q, the contrapositive for this implication is negation Q implies negation P. So let's say we use the same P and Q, which is P, she is hungry, and Q, she is it. So for the contrapositive of the implication P implies Q, which is if she is hungry, then she eat. The contrapositive for the implication is if she not eat, then she is not hungry. So this is the contrapositive for the implication, which is negation Q implies negation P. So what is inverse? For implication P implies Q, the inverse for this implication is negation P implies negation Q. So for more easy to us to understand, let's just use the same P and Q, which is P, she is hungry, and Q, she eats. So the inverse for this implication is if she is not hungry, then she not eats. So this is the inverse for the implications P implies Q, which is negation P implies negation Q. So here you can see the truth table to prove converse, contrapositive, and inverse. So P and Q there is a statement, while negation P and negation Q is not the P and not the Q. And P implies Q, just like what I said. If she is hungry and she eats. And Q implies P is the converse for the implication, and negation Q implies negation P is the contrapositive, and lastly, negation P implies negation Q is the inverse. So here you can see the truth value, which is true, true, false, false, true, false, true, false for the statement. With tautology, what is tautology? Tautology is a compound proposition that is always true. Like truth value is always true if we check on the truth table, while contradiction is a compound proposition that is always false. There is no false in the truth value, all false, while contingency is a compound proposition that is neither a tautology and nor a contradiction. Not all true and not false. They still have true and false in the truth value, while for tautology there is no false, and for the contradiction there is no true. So this is the truth table for R implies R or S. You can see here the truth value for statement R is true, true, false, false, while the truth value for statement S is true, false, and the next column, which is R or S, if one of them is true, then the statement will be true. For the R implies R or S, if R is true and R or S is false, then the statement will be false. But here, you can see all of the truth value for the column is true, all true. So this is what we call a tautology, which is all the statement here is true, have no false here. Okay, for the statement, for the implication, this is the truth table for R and S and negation R. So here you can see the truth value for statement R and S is still the same. So for negation R, if the truth value of R is true, then the truth value for negation R will be false. So we go to the next column, which is S and negation R. So if one of them is false, then the statement will be false. So if you can see here, only if R is false and S is true, the statement will be true. While for the next column, which is R and S and negation R, all the truth value is false. So this is what we call a contradiction, that all statements are false. Here is the truth table for R implies negation S and negation S. So here you can see truth value for statement R and S still the same, and negation R, negation S is just like the converse of R and S truth value. So we go to the next column, which is R implies negation S. So here, if R is true, then negation S false, the statement will be false. So that's why you can see here, only if R is true and negation S is false, then the statement will be false. We go to the next column, which is R implies negation S and negation S. Here you can see there is false, there is true, not all false and not true. So this is a contingency. Some statements are true and false. So logical equivalent. Logical equivalent is a compound propositions that have the same truth value in all possible cases. For example, P and Q are logically equivalent if P equivalent to Q is a tautology, which is the truth value for both of them is all true, have the same truth value. So we call logically equivalent. But what if for contradiction and contingency? So if uh, both of them is have the same truth value, even uh, that is a contingency or contradiction, but have the same true value, it is still called logically equivalent. So here you can see the equivalent symbol, P equivalent Q, P equivalent to Q. So here is the example for equivalent. Q implies P equivalent to negation P implies negation Q. So from here you can see Q implies P is the converse, while negation Q implies negation P is the contrapositive, and negation P implies negation Q is the inverse. From there, you can see Q implies P, which is the converse, and the negation P implies negation Q, which is the inverse, have the same truth value, which is both of them true, true, false, true. So this is what we call them logically equivalent. So here we can prove that Q implies P is equivalent to negation P implies negation Q because they have the same truth value. So for example 2, we can prove that P implies Q is equivalent to negation P or Q. As we can see here, P implies Q and negation P or Q have the same truth value, which is true, false, true, true. So this is logically equivalent. But if like the true, false, true, true have in another positions like true, true, false, true, so that is not equivalent. I mean, like both of them not equivalent to each other if the position of the truth value is different. For example 3, we can prove that P and Q is equivalent to P or Q implies P and Q. As you can see here, P and Q and also P or Q implies P and Q has the same truth value, which is true, false, false, true. So this is another logically equivalent. To solve any logical implication, we should refer for the precedence of logical operation. So for any operator that have more precedence value, we should prioritize them first. I mean, like we should solve them first, and then we solve another operator that have low precedent value. So here is the law of logic that we learned from Mat222. First, double negation law. 2, De Morgan's law. 3, commutative law. 4, associative law. 5, distributive law. 6, idempotent law. 7, inverse law. 8, identity law. 9, combinations law. 10, definitions of implications. 11, definitions of biconditional. And the last one is absorption. For example 1, which is P double implies Q and P implies Q or Q, to solve this kind of questions, we can start with definitions of biconditional. As you can see here, there have P double implies Q, which is P can implies Q and Q can implies P. So that's why we use definitions of biconditional to separate them. And then we use commutative law, which is we can change their positions. From P implies Q, we can change to Q implies P because they still have the same value. And then we use associative law, and then we use absorption law from associative law, and then we use definitions of biconditional, which is P double implies Q. We combine from P implies Q and Q implies P to make it short. Example 2, which is negation P or P and Q and R implies P or R. Here, firstly we use absorption law. We absorb from the questions, and then we use definitions of implications, and then we use De Morgan's law, and we use associative law, and then we use inverse law, which is we inverse the implications from the implication that we associate them, and then lastly we use domination law, which is from P or D naught to D naught, which is we can change to D naught only because they have the same value as we refer from the. For example 3, to prove that P implies Q is logically equivalent with negation Q implies negation P, firstly we use definitions of implication, which is from P implies Q, we change to negation P or Q, and then we use commutative law to change it from negation Q implies negation P, and lastly we use definitions of implications. We change from negation Q or negation P to negation Q implies negation P. So here you can see negation Q and implies negation P is the same like P implies Q. So them is logically equivalent.